Hi, good afternoon, everyone. Hoping you can hear me now. Hi from Brisbane, and some great talks this afternoon. And yes, time for mice. And what I wanted to do briefly was give you a little bit of an overview about the various mice projects you'll be hearing about. And to start off with, why mice in particular? One of the reasons that this is my preferred sort of approach for doing some of this modeling is that really it's focused on some specific questions and key components of the ecosystem that you need to look at to answer a particular question. So they're intermediate complexity. They try to find that sort of sweet spot where there's not too much or too little complexity included. But very importantly, these models are fit to data. So they're not a mechanistic model in the sense of describing every single process. What they try to do is come up with a simple population model that is consistent with all of the available data and information. And because it's a dynamic model, not a static statistical model, you can look at trends over time and a number of different hypotheses. So these sort of models are validated models. They're similar to the sort of stock assessment models, if you like, that one might use to give tactical fisheries advice, but they incorporate some additional complex interactions from ecosystems. So they are increasingly being used in both Australia and internationally. So one of our earliest mice models was developed with my colleague B. Morello, where we started off focusing on a single reef on some of the key categories, namely the interaction between COTS of different age or size. We used age because that's simpler, and their interaction with different coral categories. These models, as I said, are fitted to the available data. So we can use any data that is available. In this case, the early models were fitted to the LTMP data. And really, as you can see from COTS on the left, we have to first of all have a population model that adequately describes the sort of dynamics we see. And we can play with different hypotheses. So these models are very good at allowing you to address uncertainty, to try different hypotheses and to see if they're consistent with the data. With a coral, for example, this helps us to parameterize how that interaction between the COTS and the coral happens, as well as showing things like what is the recovery time for the large, slow-growing corals versus the fast-growing corals, for example. So this was the basis for this work that you've heard a little bit about around the ecological thresholds. So for example, if you start on the right-hand side of the slide, if we have a lot of COTS relative to coral, the coral is obviously going to decline. When you get to a point where the coral growth matches the COTS that's busy eating them, how much is being eaten is sort of compensated by the growth, that's when you have this equilibrium situation. And so that's what we define as the threshold. So if you can reduce the COTS to at least that level, preferably less than that, then you're in a situation where your coral growth outpaces your COTS grazing and the coral is able to start recovering. We've mentioned as well that there's a slightly lower threshold, which we've called the reproductive threshold, based on Jacob Rogers et al.'s work. And that is one where you're basically collapsing the reproduction of the COTS, and so you're allowing a much faster recovery of the coral. So these sort of models have implicit in them the density dependence that happens in the coral, as well as some of the density dependent factors that affect the COTS populations. So that's the basis of being able to construct these curves, which basically the sort of results we've been giving you come out of curves like this. On the horizontal axis, we have how much coral cover is there, and this is the one for the fast-growing coral cover. And so, for example, if you look at the red dot, that would have been from a Keesing and Lucas study where the average coral cover was about 35%. And then the vertical axis tells you what the COTS density that is that equilibrium threshold point that I told you about. And you can see a few things from this, which I've summarized in the next table. It's really that these ecological thresholds are complicated. And this is sort of why Cameron was saying there's scope to improve how we sort of use these in our decision rules. The first thing is that with different coral cover, the threshold changes. So your threshold's going to change based just on the actual cover. It's also going to change based on what kind of corals you've got. Then there's the fact that we have this poor detectability of some of our small COTS. And so we're suggesting a number of COTS be removed and that you reduce it to a certain number, but we know we're not actually seeing all of the COTS out there. And this is the sort of thing that these kinds of models can help one with this cross calibration. So with this table here, it's from a paper we just recently published. And I've pulled out a couple of examples to show you what some of those calibrations look like. So if you have your coral cover percentage is very low, say 15%, then the ecological threshold from the study, if you go all the way to the right-hand side, in terms of the CPUE, the catch per unit effort, the COTS per minute that the culling divers are removing, that number, threshold number, is 0.04. But we can cross calibrate that to some other statistics. So if you go one column to the left, in terms of the actual large COTS that your diver will see, they will be seeing 3 COTS per hectare. So we're converting between CPUE and the COTS density. But this work also shows that actually they're only seeing a very small number of the COTS that are there. So the model can tell us that the actual number of COTS there, for example, would be 48 per hectare. And that number comes out of having the mortality, the dynamics of the COTS all fitted to the data. So we have a good idea of if you're seeing a certain amount, how many smaller COTS are there and how many are cryptic and hidden that you can't actually see. And if you look down that table, you can see that those thresholds change as you have a different coral cover. And also the CPUE COTS density relationship is not linear. This work suggested that the small COTS, the detectability was about 19%, and we used for the larger COTS the detectability of around 82%, which Morgan talked about earlier as well. So these sort of models, because we have carefully calibrated them and validated them with data, they provide quite a solid basis for us to sort of cross compare between these kind of statistics and look at under which conditions should we do better. So this was sort of the starting point, and after my talk, Jacob will be following with some of the ways in which we're trying to take this a little bit further. So one of those is to do much finer scale understanding. So to look at not only per reef, but to look at the actual sites or zones on the different reefs, as Cameron was explaining with, which site do you go to first and so forth. Can we do better in terms of the rules and algorithms that tell us where we should go? Can we change that dynamically? So based on, what we're finding there, what's the optimal threshold so that we're making the absolute best use of the limited resources that we have. There's also other important factors we've heard a lot about at this workshop, such as the importance of fertilization success and spawning. How can we test how to do better with these rules? And these models can integrate all of these factors. We also have Amy Despians is joining our modeling team, as well as Laura Blamey, looking at different coral communities and benthic structure and how we should modify these rules. Jacob's going to tell you a little bit about what this looks like under changing climate, for example. And then very importantly, as part of the CCIP, I think we've all recognized the need to sort of seamlessly integrate between the different data sources, the different reef scale models, as well as the large regional models like Carlos just talked about. And for example, the mice model I showed you has been embedded in the COCONET, the regional scale model, and we in turn look at those regional models to test what, different recruitment to different reefs and how that changes the sort of rules and advice that one might come up with at that reef. So just to give you another idea of some of where this work is hopefully headed, Laura Blamey previously led some mice work focused on a cold water reef. And this was a nice example of where there were certain
Eva, we can't hear you, so if you're still talking, maybe you can hold off for a second and we'll check the audio, or check you're not muted. She can't hear us either. Someone write a big sign and hold it up to her.
Oh, hello. Can you hear me now? Sorry about that. I'm not sure. I think my speaker battery died. I'll just wrap up and take any questions if you missed some of what I was talking about, given the time. So just to summarize some of those points, we're basically using these mice to integrate all the available data and understanding into sort of one dynamic framework to help support management of, when, where, and how can we do better. So, for example, we can use these mice to come up with dynamic optimization of ecological thresholds. So we could modify the sort of rules we currently have on the on-water tools based on what the site is, what the coral cover is, how much bleaching there's been, aspects of the spawning behavior, and so forth. We can link in predators and no-take areas to help better understand their role in promoting the resilience of the system, for example. We can link with and changes in the habitat and reef substrate due to climate change to try to also help our understanding on how we can do the best job in controlling the COTS. And so I think I'll leave it there because the next presentation builds on mine by Jacob Rogers, giving you some more specific examples of how we've taken some of this nice work further. So just to end by saying thank you to all my co-authors and the many people we've collaborated with over the years, as well as to my airport buddies from yesterday's 4-hour wait at the airport. So thank you.